Remember what we're doing with chip-level multiprocessing. We're essentially putting the whole computer on a chip, except for one important thing: the memory. Right? That's the one. It's a bummer, but it doesn't fit. But everything else goes on. So I love about what CMP design is about, how to manage the system. That what used to take like a room this size or the whole building is now fitting on a single chip, and that doesn't mean these things don't interact, are not prone to live locks and deadlocks and overpower conditions. So how to manage that is very complicated. And the big difference between the building size system and the chip level system is the time domain. What used to happen over many microseconds now happens in nanoseconds or picoseconds. And so the reaction time to a overpower condition is very different. And so much of this is moving to hardware and of course in collaboration with software. Some of you may be familiar with like ACPIP, which is how the sort of operating system can give there's a hardware some guidelines for how to manage power. And I think rather than very specific directives for what to do, what we're going towards is sort of policies that optimize power within these, where optimize performance within these power levels is a typical requirement. But there are enormous benefits to this evolution, and I think most of us would not be in this business if this integration had not happened, and it's just an unbelievable ride. So as you go to on-die, if you just look at the interconnects on-die, and I'll spend a fair amount of time on the interconnects on-die and also on the cache organization on-die. You're going to terabytes per second of bandwidth versus between chips, you have gigabytes per second. The latency now becomes nanos in a handful of nanoseconds as opposed to hundreds of nanoseconds. And the power consumed by communication is milliwatts rather than watts. So you have several orders of magnitude in each of these. The on-die cache, if you have cores sharing cache, you can have very fast communication. Your hit rate goes up. I'll show you some slide with some data for that. The time to synchronize between cores around at the barrier synchronization is much less, and you get better cache effects. You get rid of some cache effects like false sharing. If you attach memory to this single socket, even if you can't integrate it, it simplifies the system designs. You get less NUMA effects. You can simplify application development and performance tuning. And on-die performance scaling can be almost linear with the core count. So the cartoon there is actually a fairly accurate description of how most Intel chips work now. You have most of the chips you're buying, like a Haswell or an Ivy Bridge or a KNC, have a ring interconnect inside the chip. That may be a secret, but no longer, I guess. So and our group did a lot of work on that, so I'll talk a bit about that. So here you have, along on the top and the bottom, you have processors attached to a ring interface. In the middle, you have a third-level cache, which is distributed around the chip, so that each segment of the cache shares a ring stop with a processor. And basically, yeah, I'll get to that. So and then you have memory controllers and network controllers, I/O, PCI Express attached to this same ring interconnect. So so this is the example. So what basically this interconnect is a pipelined ring-shaped pipeline bus, and it connects the processors with the cache and to memory and to I/O. The bandwidth on this is roughly the frequency with which you're clocking the ring times the width of the ring times the number of stops, because you have different data on each segment. Because that's a little fallacious, but I'll show you in a second. Because of course, the longer you go, the more stops you have, the longer you may have to go, and so that increases your occupancy, and that's basically reduces your bandwidth. So this is basically the frequency. You divide by the distance, the average distance a packet has to travel on the ring. So a single ring going one way is pretty nice, but if you have a choice, if you run out of bandwidth and you have a choice between widening the ring or running the ring twice as fast, or adding another ring in the opposite direction? What's better? If you're out of bandwidth on this interconnect, and you want to increase the bandwidth, double the bandwidth, would you have two choices. Would you make this ring you have twice as wide, or would you add a ring in the opposite direction of the same width? And the reason is that you want to do the opposite one is that when you add a ring in the opposite direction, if you always pick the shortest distance, you cut your occupancy in half. So actually adding a counter-rotating ring not only doubles the raw bandwidth, but it also doubles the effective bandwidth, because you cut your occupancy by half. That observation almost got me the Turing Award. But so another effect is that on die you can have a very wide interface. In fact, typically this ring interface has like close to 2,000 wires, and it goes all around the ring. And on die, that of course is pretty minimal. In fact, you can actually route these wires over the caches, unlike the picture. So they don't really take any area. You can add more specialized rings in addition to your data rings. You can have address probe rings. You can have invalidate rings, acknowledge rings, whatever you want. On die you can do power encoding to minimize power transitioning. So as you look to see how many bits are changing from the previous packet, and you choose what the encoding of 0 or 1, depending, to minimize the number of transitions. And that's particularly important for DIDT problems, where the worst case is that all your transmissions go from all zeros to all ones in one cycle. But if you do power transitioning, the worst case, that transition has actually no effect, and the worst case actually is where half the bits are switching, and so you cut your DIDT effect by half. So the ring latency, of course, increases as you add ring stops, but we're still talking nanoseconds, and compared to going to main memory or to the network, this is pretty minimal. And notice that the important thing in cache design and on-die interconnect design is to minimize trips outside the chip to main memory and to the network. And so spending a little bit of extra time inside the chip is usually a good deal. If you compare a ring interconnect which just has uses the periphery, of course you could argue, well, wouldn't it be easier if I had a mesh and I could go anywhere I wanted in the middle? And it turns out that the worst case is the red path there, where you're going from the middle of one side to the middle of the other, and you have to go all the way around instead of going straight. But for most other transactions, it's really a wash. Okay, so I'll show you a picture. So here you have the cores outlined. You have the caches in the middle. You have the on-die interconnect outlined over the caches. So here you have in core number 0, I just had a cache miss, and I want to access the large shared cache. Something. Oh, there goes the request on the request bus to the cache in question. And the address gets sent out over the cache. The data, of course, is aligned with the wires on this very wide bus. And so there's no collection of the data there, except at the very end, of course, the data goes back up into the L2 cache in core 0. Is that neat or what? That's all inside the die. Actually, not from 15's own cache. It's just that the core number 15 is co-located with a slice of the shared cache. Okay. So you have a distributed cache. So you basically decide how you go to or which cache you go to. You look at the low address bits, or the address bits just above the byte within the cache line bits, right? So say that the cache is striped on cache line boundaries, then, and so you look at those bits. Of course, we actually hash them, because if you don't hash them, you're prone to hotspots, and everybody wants to go to the same place. So you do a little hash, and you get to the data. And actually, this is a slide that describes the Knight's Corner chip that Intel is shipping now, and we talked a little bit about yesterday. There's a difference here, is that in this case we still have a ring, and you see the memory controllers, the cores with their level 2 caches are associated with have a ring stop on the ring. what we did there was since this chip was actually originally designed for graphics, and you ran out of space, so you decided that in graphics a large shared cache is not that valuable. So we took instead of having the large shared cache in the middle, we took the data portion out and left the directory and the tags in, so that now, if this guy misses in his L2 cache, he looks again at the low address bits, decides which tag directory to go to, and the tag directory will tell him which core, if anybody, has a copy of that data in its L2 cache. And so you use the same principle, but instead of getting the data right out of the L3 cache, you now have to go and get it from some other core, or you have to go get it from memory, in which case the tag directory will request it. But actually, this shows that the ring interface actually scales to about 60 cores. So you have like 60 stops on this ring, and it works pretty well. So here are some ring design considerations. The one is the flow control. We use what's called the rotary rule. So you basically only arbitrate once you get on the ring. To get on the ring, once you're on the ring, you have the right of way, and you can just zip right along. And this allows you to just basically take a single cycle per ring stop, and there's no store and forward, no further arbitration in the ring. What happens, of course, the bummer would be if the target cannot sync the request. Now a typical traditional network problem is what do you do when you can't complete the transaction? Any suggestions? So one good thing about rings is that what goes around comes around. So you could leave it on the ring, right, and hope that the next time it comes around, there is room in the buffers to sync it. And that actually is not an unreasonable request. It's not a great method because presumably you couldn't sync the message because there was congestion, and now you're adding to congestion to deal with the congestion, and it's not great. So a step beyond that would be that, of course, the node that put the message on the ring will see it come by the second time, all right, and so he could snarf it back off the ring and say, I'll hold off a little bit, back off a little, kind of like Ethernet arbitration, and wait till things clear up a little bit. You could also have debit credit systems, which work but have also some downsides. The routing algorithm is basically our experience is we pick the shortest way. Since you can go two directions, we pick the shortest one. That's a greedy algorithm. It's not the best for the worst case. It minimizes the best case latency. It's not the best for the worst case traffic, like a tornado pattern where everybody is going a few hops to the right. Now, one ring is totally unutilized, and everything is just hop. In fact, if the traffic is heavy enough, it's a horrible behavior. In basically sort of general cache algorithms, that is very unlikely to happen, especially if you, as I said, if you hash the allocation of memory blocks to the ring. You could also be more clever. We actually rarely found the need to be more clever than what I've already described, but you could have adaptive algorithms. You could look at how many entries are in the queue going right, how many entries are going in the queue going left. You weigh that by the distance you have to go, and you find some optimal trade-off point to go with. People are inventive, right? So you want to expand to different kind of ring topologies, and as long as it matches the layout rules for a chip, all kinds of things are possible. You could have this is fairly obvious. You have two rings. The reason for two rings is that you could now cut the latency or cut the number of hops to the node you want to go to, as long as it's on the same ring, and you only cross here. But of course, the downside is that this is a collision point. Not everybody can have just free ride through there, and so you need buffering, you need back pressure, you need flow control, and so life gets a little more complicated. You could you could have sort of subdomains, say where you go down here, a message comes here, you go down here if you need to go there, otherwise you go straight across, and you just arbitrate in ways that make sure that what comes up here doesn't collide with what goes up there, and that's you can do that in rather crude ways and get a pretty good. You could do affinity caching, where you basically says instead of having one big distributed cache, have cache domains, so that these cores share this data, these cores share that data, and so now data brought onto the chip from memory could go in either of these 4 caches, and now of course you're cutting down. The advantage is you're cutting down on the distance that you're going, and you're reducing total traffic, and in a very large chip with maybe many dozens of cores, this is a reasonable strategy. Yeah, with an alternative to leaving it on the ring, would you look to the neighbor to see if he has some room in his buffer to hold this packet, and then later on have him just smuggle it across to the destination. I think that's a good idea. It's something worth thinking about. It has many consequences. Of course, it sort of assumes that he has the buffering space, and since you have a single cycle to decide whether to get off the ring or not, you can't. You can't quite take the time to model the world economy before you make a decision, and so it's not so easy, but it's a plausible solution. And because as I said, it's pretty critical to it's a difficult problem. So the trivial solutions don't really work, and so you have to be willing to think about it hard. Of course, you could have a mesh of rings and in each direction, and now you get sort of the benefits of this, and you could kind of scale it forever. The challenge is what happens at the intersection points here, and so typically what you do is you do dimension routing. You try to minimize the number of times you turn a corner, because so long as you're on the ring, you have the right of way and you can just zoom right along. Once you turn a corner, you have to arbitrate against the people or the packets going in the opposite direction, and so you try to. This is a research chip that Intel did a few years ago. It's not a product, but it is a little interesting. It was called Polaris was the name of the chip. It actually got teraflops performance on a single chip. It basically has a bunch of floating point multipliers sitting in a mesh. Here's actually what each slice looks like. So you have the compute elements. You have a router goes north, south, east, west. It also goes straight up, so you could put memory on top of this chip and actually get your through silicon via stacked memory, and you put all of these tiles together. Well, if it did animate, it would have sort of shown that individual slices on this die could go to sleep. Even within each slice, you could have pieces go to sleep, leave the router running, but have the memory go down. And so you had various power levels where you could turn memory completely off. You could leave it in a state where it would remember its data but could not access it, or you could run at full tilt. And so this is sort of, I think it illustrates the type of problems that Intel looks at studies to make these chips work as well as possible. So you try to save power in elements that are not fully utilized, and you of course apply the power to the cores and vector units that are busy. I should clarify. I said yesterday that KNC gets about 7 gigaflops per watt, and I did say also that that's only for the chip itself. Okay? Some of the astute listeners said that that's not quite right if you include the power consumed in the memory system, in the routers, in the networks, in the power converters, in the distribution of the power system. And he said that he looked it up, and another report said that was about 4 gigaflops per watt, which I totally agree with that you lose at least 50% of your peak flop rate per watt as you include all these other components. But this one is actually 16 gigaflops per watt, and I bet you when they calculated that, they only did it for the chip itself. Now, do you remember what the goal is for exaflop at 20 megawatts? 50 gigaflops per watt. So actually some applications scale almost, the performance scales almost linearly as you go from 1 to, in this case, 16 cores. And these are actually some measured benchmarks. So while it does very well in many ways, it makes power and cooling more difficult. Memory bandwidth, as we talked about yesterday, gets more difficult. Memory capacity per core gets more difficult. Somebody asked me, well, it's well known that it's going to go down. Well, actually, it's not obvious to me that it's going down. It's more like, I think it's a trade-off. If you may have to try harder or pay more for more memory capacity to still make it work in this environment, but it may not be the right thing to decrease capacity per core, because it may be the most beneficial to your application. Network and I/O bandwidth gets more difficult because you're trying to concentrate presumably network bandwidth is somewhat proportional to the performance of your node, and as well as maybe the number of nodes in the system. As that performance goes up, your network bandwidth needs to increase. The cache capacity also is fighting with cores for space on them. Not everything worth doing is worth doing to excess, and so chip level multiprocessing, and maybe some limit that says maybe there may be a sweet spot here that after your efficiency, your performance per watt, your performance per area may actually start going down as you keep piling it on. Some of the benefits that we started with, reasons why you want to be on the same die, it may actually, of short communication, short latency, is you start losing it because there are so many hops, the network gets so large, you get so much congestion. Yeah, so I kind of showed you this picture yesterday, but this would be kind of what a mesh looks like. This is with 128 cores, and you have the inner core, the vector unit. You have a local cache, and you have a slice of a shared cache. And so one of the things that I wanted to show you, but I don't have time for, is you want to manage. Given that the shared cache, you own a slice of the shared cache as well as you own your last level private cache, and it could actually easily be made out of the same cache blocks, and so you could manage the boundary between the shared cache and the local cache, and it maybe have a big impact on performance. In a way, when we talked about the value of heterogeneous computing, probably the biggest bottleneck that your thread is encountering is memory access. And so giving it more cache to your critical thread may be much more beneficial than giving it more floating point units or a bigger branch predictor or something. So, and this is something that's very practical to do, as opposed to putting a mix of cores on die, because you can do this dynamically as you predict, as you discover which thread is the last one to reach a barrier or due to load imbalance or whatever the problem is. You asked I don't forget your name, but one behind Paul is asking very good questions about power and stuff. So you ask about how much power does it take. This is actually simulated, but this is for KNC. Caches for or against, and there's a little argumentative against NVIDIA that they don't say caches are worthwhile. But caches, if you look at the two columns here, one is the bandwidth between what you can achieve between memory and caches, and then there's a relative bandwidth per watt if you go to memory versus cache. So the yellow is memory, the blue is cache, and you see there's a dramatic difference in favor of caches. Of course, the capacity goes the other way, so you know that, and there's nothing without a trade-off. So actually, my group, now I'm running out of time, so my group we're firm believers in caches and cache coherence, and so I did want to show you a little bit about our schemes for cache coherence. So when you have coherence but there's no sharing, you really want minimal overhead. You want the transaction to just fly and don't want coherence to get in the way. But when there is sharing of data, you want hardware coherence to kick in and make it invisible to the application, that they're actually the data is actually bouncing around in the system. And because the cost of doing that really shouldn't be compared with no coherence, it should be compared to the cost of managing your data when you have no coherence, having locks and barriers in software to make sure that you don't have race conditions, you don't collaborate with other data, you don't leave stale data, flushing out caches and flushing out TLBs to make sure you don't leave stale data behind. All of that has power cost, and if you can avoid it, it's a good deal. But in order to have coherence, you have to keep track of where data is, and one historically default approach is to actually put a bitmap in memory. With each cache line in memory, each 64-byte block in memory, you also keep some bits that tells you which cores have a copy of this data. And then when the data is accessed, you look to see if anyone has a written copy, and if as you divide out you dole out shared copies, you set another bit to keep track that this processor has a copy, and which needs to be invalidated if somebody writes it. The trouble with that is that it basically reduces your effective memory bandwidth by a factor of 2, because you not only had to read the data, but then you have to write and to update the directory bits as well. So that's a bummer. And since we work so hard, memory bandwidth is so expensive, you hate to pay that price. You could have, there's a fairly popular, I think it's called SCI, Scalable Cache Interconnect, something like that, which keeps track of, or it has a linked list of who owns a particular cache line. That actually is reasonably popular, but it's very slow. If you try to update the list in the middle, and there's a lot of traffic. I think as long as you don't share, it's actually quite efficient. But if there is sharing and the level of sharing is modified, then there's quite upheaval. You could have invalidate rings that just tells everybody, be broadcast when you need to do a cache update, and everybody looks at it. That can be also be a little expensive. The thing we're looking at is what we call hierarchical organization, where it's kind of what I showed you so far kind of sets the backdrop for this, that you have a tag directory that keeps track of so you have multiple levels of tag directories. And so here, imagine here you have the cores on a die. So say this is a partition cache. So all the cores in this row shares one version of the last level, one segment of the last level cache. This shares another one. And now this red tag directory keeps track of who in this row has a copy of a piece of the data. The blue keeps track of which row in this chip has a copy of this data. So this is, you get, instead of getting an n squared growth in tag directories, you get an n times log n growth in tag directory, which anytime you go from n to log n, you're very happy. And so what happens, say we always start with a core in the top left corner. He wants to read, he gets a cache miss, and he wants to get the data, and he wants to know where to get the data. So he sends a request to the core in his row that knows who has a copy of this data. So he then decides that there's a third core that has a copy of the data. He sends a message to that core. He picks it up, reads it in his cache, and sends it to the core that had the issue to begin with. Now suppose you want to service it from memory. Again, you have a miss on that same address, so you go to the core that he decides that nobody in this row has a copy of this data, but he knows which column, blue directory, he's now in the right column, so he goes to the directory in this column that knows who, if any row on this chip has a copy of the data. In this case, he decides nobody has it, so he makes a reference to memory, which conveniently is located just off that row. He sends the data across here and up there. Notice he doesn't backtrack the same path. He goes right over to minimize the number of turns in the mesh, and so you get. And the other thing here is that the bad things in a mesh like this is the turn. So when you turn is when we also look in the local directory to see where to go next. So you're combining two sort of evil effects whenever possible. And so you minimize the ring thin, and in essence, you end up with, of course, you have the Manhattan distance, but you're not inserting extra stops. I'm running out of time, so I won't talk too much about it. I want to show you a picture here. This is some analysis with the bioinformatics benchmark. So sometimes people say, well, what's the value of sharing caches? Because my application doesn't share any data. So what we did was we studied that as the caches get bigger, the reason why you're not sharing any data is that your cache is too small. So as you get bigger, the yellow component, which is data accessed by all 4 threads, is actually growing. As you go from 4 megabytes up to 64 megabytes, the yellow component is growing. And this is for different benchmarks. It's a little different from each benchmark, but it's quite typical that the larger the cache, the better your sharing works. Here's another experiment that suggests how often are things accessed. So it turns out that the shared data is accessed a lot more than non-shared data, and so it gives you so just whether you're hitting on somebody else's data is only a small portion of the total problem. Here's a similar issue that on the top picture you have 4 megabytes caches per core, and you look at how well your cache misses go. On the bottom one, it's the same program running they're called SEMFI. It's a bioinformatics benchmark. On the bottom line, you see if you have a single shared cache, and you see the cache miss rate drops dramatically. That's actually the end. But I had some bonus slides for you because somebody asked me some questions after the talk yesterday. So here is a cache allocation algorithm. I don't have time to go through it in detail, but basically, I mentioned you can sort of adapt. If you have this slice of the total cache co-located with your core, you can sort of manipulate that to allocate space in the cache to yourself versus to you can grab space from the global shared cache and use it for your private cache. And so, of course, so we have hardware that we call it the gradient placement algorithm. And this is without it, and this is with it, and of course this only makes sense if you also looked at the slide with how this results in better performance. But here, with this algorithm, which is also pretty good and much better than no algorithm, you get these dips where applications that don't make much progress are just hogging the cache and messing up everybody else. In this case, with this gradient placement algorithm, you adjust yourself much quicker, and it works remarkably well. Actually, that is in some products. As I said, I worked on some alpha processor as DEC. Here's just on scaling example that I flashed by you, where it said that EV5, which was the fastest microprocessor in the world in the mid-90s. If you had scaled that forward, you could now fit 1,000 of them on the same size die. You would have it would run at 9 gigahertz if you scale, and the power would be about 1,000 watts if you and that's even without because that assumes in this slide that we stop scaling the voltage at 0.5 volt, and which is a reasonable limit, and so power is the problem. Of course, there are other issues here before you discover them. I have to tell you that. Of course, when you add multiprocessing onto a chip, there's overhead, and the overhead is proportional to the number of cores you have, the performance of these cores, the frequency, and so it grows. Traditionally, performance of cores grow by when we could increase performance, we really only got performance growing by the square root of the transistor count. When you couple that with the fact that the transistors got the square root of 2 faster, 1.4 times faster, and the IPC increased by 1.4, so 1.4 times 1.4 is 2x, which sort of says that Moore's law doubles performance every 2 years, even though his law basically says I double the transistor count every 2 years. But then architects sort of squeeze that increase in performance out of the more added transistors. But now with CMP, you could sort of, in theory at least, get linear increase in performance by adding more cores. And now, in this area where the two curves meet is where it's interesting to think about, should I increase the performance of the single core, or should I add more cores? And because you're on similar curves where the yellow curve is tangential. I think that's it.